Okay, cool. We're going to get started. So I'm going to introduce Rusu. I hope I said it right. He's from the Bay, San Francisco. He lectures at Stanford and is the CEO of Open Perception. And he's going to talk to you today about perceiving the world through the eyes of a robot. So take it away.
For the introduction. Can everyone hear me in the back? Great, perfect. Okay, excellent. Thanks for the applause. That was much appreciated. Hi, everyone. This is my first time in Urbana and Champaign. So, I've heard a lot of debates about Urbana and Champaign. I'm not going to go into that. They were covered this morning. We covered that thing. I am going to talk to you about a bunch of things, well, mostly from a perspective of robotics. How many of you know what a robot is? Cool. How many of you have taken like robot classes of any kind? Okay, that's good. So probably I can skip this slide. You know what a robot is by now. So there's a few devices already available in the marketplace. Some of them are still research products. So you might have seen the Google autonomous car driving around, or you might have heard about the DARPA Grand Challenge and Urba Challenge. And there's a bunch of other products being developed all around the world in research university labs, such as robots with manipulators, right? And we call these robots mobile because they also move around. They're not like fixed like the ones in the industry. So I actually noticed this. This is part of your curriculum or something. I was quite impressed to see this, Technograph newsletter or whatever it is in the other building. So you guys are definitely familiar with this kind of stuff. The way I'm going to go through this talk is, first I'm going to explain why mobile is important, like what is mobility and how does that affect us as a society, and then kind of go into the nitty-gritty details of how to make that happen. So the mobility problem, and this is just like a short, like brief introduction in the history of mankind. One would argue that before we could travel, the humankind was blind, right? We only saw as far as we could travel in a few days. And because of that, we had like really crappy, really shitty maps. Like, and this is an example right here. That's how they thought the world would look like, right? Because they would travel for like, in horses or something for like, 1 week and they would die. And that's how much they could map, right? And so that basically leads to a minimal interaction, right, between, different nations or whatever, different tribes, whatever they had back then. Excuse me for that. So later on, they started using points in the sky as a reference to basically map. And then with that, they were able to create more comprehensive maps, such as this one. So this is around, 16th, 17th century, closer to us. And as you can see, there's like still a lot of mistakes here because, if you look at the Americas, they're like this like big, gigantic blob here. South America is like really crappy. And then they didn't know anything about like what's happening down south, right? So again, but because we had better maps, this led to an accelerated international trade. So, and also, in some sense, evolution in terms of social and scientific progress. And that brings us to today. And, all of you are probably on Facebook or Twitter or LinkedIn or Zynga or you name it, right? And because we have this mobility in terms of like getting data back and forth on the internet, that leads to an increasingly hyper-interactive culture, as we call it. And again, that's part of progress. So in some sense, if we look at robots and, whatever the evolution of mankind, we could say that, step 0 was I could only see in my backyard many, many, many years ago. Then we had human navigation. We could go around. Then much later happened this, in the 18th century, the industrialization period, the part where as a society, we started basically getting more and more, so more needy for more products, and that led to the introduction of industrial robots. And for those of you who haven't seen many in action, there's many of them all around the place. Like, every factory right now, we can't imagine our society not depending on these industrial robots. But what I'm going to talk about is how do we move to the next step, which is robot mobility, which is basically a next generation of personal robotics, like, for each and every one of us. So this is what I meant by, let me just move this video right here. So this is your typical industrial manipulator, which go from place A to place B. It's pre-programmed. It does it very fast, and it does it like, million times a day, right? And this is what helps us kind of like build many, many different products and ship them all around the world so that we can consume them as I think. But really where we want to go is something along these lines. And bear in mind, this is teleoperated, so there's actually a guy with a joystick behind it. And so he's really good, by the way. This is one of my former colleagues. And the video is sped up, right? So like 10 times or even more. But in terms of a robot that does things for us at home, this is where we imagine the future to be like, right? So you have a kid that leaves toys all around the house, and then your robot just comes and arranges everything in a very nice way and cleans up the whole thing, like tidying up the room. So this is an imperative shift from industrial to personal, right? So from raw, fast, and precise to sophisticated and adaptive and safe. So this clearly answers the question, why are we bothering with all these like things, all this research and so on in the first place? During my presentation, you'll see a couple of illustrations from Eric Joyner. This is one of my favorite artists from San Francisco. His themes are very weird, like robots and donuts. I don't know why. I don't know how he mixes these things, but the pictures are really, really great. So in my opinion, robot mobility equals progress for our society. Okay, so the question is, are we there yet? Do we see all these robots like the one that I showed you, like around us? No. We really have the plan. We know exactly what we want to build. Why aren't we building it? Why hasn't that happened? What's the problem? Well, first, there was hope. And for those of you that don't know this, I'm going to play a short video. This is Robbie the robot. It's actually the first robot ever built.
Ladies and gentlemen, the robot of the forbidden planet.
50.
Now, these are his eyes. These, his ears, tuned in all directions to receive the slightest sound. And this is his brain. Robbie, turn right. Turn left. Now back to the front. Robbie, tell me, can you speak?
Yes, Dr. Morbius.
What languages?
I am monitored, Dr. Morbius, to respond to 187 languages.
Well, I think English will be enough. Now, tell me, what are your duties here on this planet?
I clean your house. I drive your atomic car.
Drive your atomic car.
I cook your meals.
Cook your meals.
Oh, cook my meals. Now,
So basically in the 50s, everyone thought that by today we're going to have this happen. Like it was just, cleared.
how do you manage that?
One introduces a sample of human food through this aperture. I have inside a small built-in chemical laboratory where I can analyze it. Later, I am able to reproduce identical molecules in any shape or quantity.
Very good. Now then, tell me, who built you?
You, Dr. Morbius,
Thank you.
and 50 MGM technicians for the picture Forbidden Planet.
Yes, Robbie, but when I want a commercial, I'll ask for it. Now go over there and shut yourself off.
Yes, Dr. Morbius.
But don't go away. We want to talk to you later on.
This is not a guy in a suit. It's actually a robot.
Ladies and gentlemen,
it's being teleoperated behind the
that
scenes.
is our robot, a housewife's dream. He's been very good on the set, done everything we've asked him to do. But I sometimes wonder, when we've finished work on stage 27 and Robbie's here alone, when the technicians have all gone home and the machinery is shut off, is he really off? Or does this machine which we have built, this complicated metal being, does it really have a brain? I sometimes wonder.
Forbidden Planet. Forbidden Planet indeed.
This is one of the oldest footage that I could actually find on the internet about robots. And there's a movie behind it called The Forbidden Planet that I encourage you to see. It's pretty cool. So I grew up in the, the next generation Star Trek era and Star Wars and so on. So these were like our personal robotic heroes. And we were all hoping that, again, like by today, we're going to have Commander Data and so on, like walking around us and helping us out. Right? Clearly, this hasn't happened. And it's funny, actually, to look in the 60s and 70s and see companies trying to build products such as these ones. And I apologize, the text is kind of blurry, but somewhere around here, they actually say what these robots would do for you and how much would it cost. And I think I see something here for like, $758 for that robot over there. They would like, clean your floors. Like that's how they were imagining these things to happen. And then like many more ads, funny ads actually. What's bringing you drinks on a small tray, like your wine and other things. And all these companies went bankrupt, by the way, all of them. So who's to blame? Like why hasn't the dream happened yet? Like what's happening here? Personally, I think there's many reasons, and we don't have the time to go through all of them and analyze them. There's a social cultural reason, mass media and ourselves, and we have like really high expectations, as you will see from my talk. There's also like problems related to funding. Like basically governments weren't really interested until recently to invest in this field. The industry is not really picking up unless there's like they see immediate profits, in the near future. And potentially there's a problem in terms of science. I mean, maybe the problems are too hard. Like we're trying to replicate a human brain, we're trying to make like AI happen, and that's probably too hard. So I'll just, basically tackle the bad side of Hollywood in terms of the social cultural problem. And I think, portraying robots as like this destroyer, like Terminator and so on, actually led to a low acceptance in many countries. And there's a lot of reports about this, and people actually fear robots. And we don't even have them yet, but they fear them. And there's another interesting thing, which is, it really depends on how you build these robots and how do you make them look like. And this is called the uncanny valley, and some of you might be already familiar with it. And what this graph sort of shows is that once you go and make your robot become too humanoid, like too much like a human, the acceptance rate drops like a lot. And this is called the uncanny valley because here you don't want to have robots that look too much like you, right? So if it's industrial, people are very familiar and they accept them. But if it looks too much like a human, it becomes creepy, right? Again, the high expectations, like we were expecting to have, robot mates. They would like teach our children or something in the future and so on. My personal twist is that it has to do with interest. I think if people are genuinely interested about a problem, they just go and tackle it. And that's what happened to a lot of the things that we have today, in terms of science and industry and so on. Really, we should start talking about a post-robotic robots generation, right? When, we're no longer like fearing them, but sort of like looking at them as like tools, right? Because that was the initial plan. We're going to have things helping us in our daily lives. And so as we're starting to kind of like enter that era, I think that's again like going to lead to significant progress in our daily lives as a society. So I come from a place called Willow Garage. And there we also build robots, obviously. And this was basically one of the first prototypes that we had called the PR2, the Personal Robot 2. And for those of you that are not familiar with it, I'm going to show a couple of videos. We have been generously funded by some wealthy investors, and we actually reached a very important milestone a few years ago when a robot that costs like $400,000 because it's assembled and designed and built in California. It's the most expensive place on the planet to build something. But we actually managed to give them away for free to universities around the world. So 11 of them went out and reached a couple of sites in Europe, many in the US, and one in Japan. And universities now are basically contributing to this like massive infrastructure, massive open source infrastructure that we built around them in the hope that this will later on kickstart a personal robotics industry. Right? So our funders were basically looking at really like long-term impact and not immediate profit. And for those of you that have never seen these videos, hopefully they're fun enough, I'll show you a couple of applications that we built.
An interface that has a menu of a number of different beers that you can select.
I'll make this,
once you select the beer,
I'll tone down the volume. So this is an application where we had a web GUI where we could order beer from our offices. Right? So this is our offices, these are our offices in Menlo Park, and we have a few beers here, and we put them in a beer bucket, and we click Beer Me, and the robot actually goes by itself autonomously to a refrigerator, matches our selection to whatever's available in the fridge, so it does like an inventory search. And then afterwards, as you will see, it kind of tries to go and grab the. We did drop 2 bottles, so that can happen. Gets the bottles from the fridge, puts them in this like small tray that we built for it, and then comes to your office and delivers beer, which is awesome. This takes roughly around like 5 minutes.
That are not available,
So,
the
you know.
robot will inform you that your choice is not available at this time. Otherwise, the robot picks the beers that
You gotta wait a little
in
bit
the
until.
fridge, puts them in the cup.
And it's funny because, you know, when we started, so we did this as part of a hackathon, like a 1-week hackathon, where we thought, you know, we could take all the tools that we built during the last 2-3 years, and then kind of like, you know, put them all together and make the problem, solve the problem. And it's actually, we discovered it was much harder than we thought, and some of the perception routines that we needed for this project we had to write during that week, so it was all like a big mess in the end. And that's why we call it a hackathon. One of the more famous videos is folding towels. This is a collaboration with our colleagues from University of Berkeley in California. So they came up with this idea that, you know, why, like one of the more important things in a household is to fold laundry. So they put together a project. And as you can see, in roughly 20 minutes, the robot will potentially fold you a towel. Right? Obviously, this is going to be very hard to scale as you have multiple towels in your house and electricity is expensive. But it's kind of cool to see that, you know, we have progress along those lines. And many other collaborators in our community basically built a bunch of different applications. Here you can actually see the PR2 trying to draw itself on a whiteboard. And again, it's just kind of like showing the manipulation skills coupled with perception and you know, C++ and Python and all the other languages that we used behind the scene to do this application. One of the things that kind of like I find this impressive because I came from grad school and we were doing robots there too, and as you probably guys are doing here, and you see wires everywhere, and once it works, like don't touch it, like take a picture and then, you know, take a video and post it on YouTube or something. Never play with it, never tinker with it. And I went to this like place in Menlo Park, and they were actually very serious about testing things. Even though it's a small startup, a very small company, you know, like 50, 60 people, they're actually very serious about like stress testing components. So this is one of the burn-in rooms where you see like components going like, you know, crazy all the time to see if a cable breaks. Whenever you change a supplier, you know, is it up to the specs and so on. And I remember we had this thing called the hot box where we put a robot inside and crank the temperature like crazy, and then we like get the robot out, and then like it's actually like sadomasochistic for robots. I mean, whenever they come alive, they become alive, we're gonna pay for all this stuff. I'm pretty sure. Upright. So in terms of kind of like the cool nitty-gritty things that go behind the scenes, the robot is equipped with depth cameras, as we call them, or stereo cameras. It has laser sensors and so on. I'm not going to go into details in that. But here you see some examples of the things that we have to solve, like recognizing objects from imagery and depth data, or navigating around in crowded environments through obstacles, or other things in terms of manipulation. So here you see like what we call point clouds, and I'll get to that in a second. And we build these object models directly from raw data, and they're in 3D and metrically correct. And we try to recognize them so we can grasp them later. So we can go with a robot and pick an object up from here and put it someplace else. So driving through really narrow corridors is actually quite challenging because the sensors that we use are precise. So we have to compensate through software and using a lot of probabilities and so on, statistics. But we can do a fairly good job in the presence of even these small obstacles like mud. What you see again here are the 3D maps the robot creates as it walks around in the world. Things that we had to solve because this robot has a couple of car batteries, so it's really heavy, like 400 pounds. But even those car batteries cannot drive like the amazingly powerful Xeon servers that we have on it and all the ARMs and so on. So in like 2 hours, they're going to be running out of battery. So that's not a really useful robot, right? But we said, well, it would be really fun if you could just like go continuously, like 24/7 and do stuff, just kind of like, you know, navigate around. So therefore, we had to build an app where we were searching for power outlets and going and actually plugging in, right? So taking one of these like power cords that we built, which does have that checkerboard on it for extra accuracy, and then going and finding a power outlet and plugging in. And using this combination of just navigating around autonomously and plugging in, we managed to, you know, make the robot go for like weeks at a time without human intervention at all. Right, so, you know, the future, hopefully it's going to look like this. Post-robotic robots, friendly robots, kind of like reading books and having fun, enjoying laying in the sun, whatever the batteries like Wall-E. Okay, so That being said, I'm going to move a little bit towards my area of expertise, which is like, 3D perception. And so I'll begin by saying that the world is not flat, yet, only like 150 years ago, there were still people that believed the world is flat, and they were trying to prove it. Like, no, let me explain. No, it's not, right? You got to go around. It's 3D. It's not 2D. And these are some interesting illustrations that it's basically graffiti on sidewalks. And it's kind of like funny to see people like posing for them. Imagine that if we would only use like RGB data, like camera imagery, like in 2D, our robots would fail, horrendously. Like you would just draw something on an asphalt and the robot would stop. Whoa, what's going on over there? Again, like it's really crazy how people pose for these things and how nice they look from certain like vantage points. How could you tell that this one is not real, actually? Well, besides the fact that it's not real. But like, how could you? Can you see any faults in it? Because I spent quite some time looking for one. That's true. That's one. That's a good observation. I didn't see that one. Actually, there's a guy or someone, like a person walking over there, like it's almost like walking on water. I think that kind of gave it away for me. And the edges are blurry too. That's true. Yep. And the shadows. That's true. See, many good observations. I actually didn't see all of them at first, I have to admit. And there's more things, like people doing it like indoors with. Like this is Nicolas Arndt, and here's another one. And also, it's great to see commercial companies going to great lengths to convince users that they should switch to 3D, whatever 3D means. So here's another interesting video.
We've been analyzing the old masters and are now able to present them in a new way. Here is the Mona Lisa. Pretty good, huh? This is her from the side. It gets better. The depth effects increase if we look at them on 3D LED TV. So the Vitruvian Man turns out to be men. Interesting. Surratt's bathers. Tranquility. No awesomeness. The Reverend Walker skating. Not much going on here, you might think. Wrong! Jeez, game over, Reverend. Premieres the girl with the pearl earring. How much cooler is that now?
So this is a commercial from Samsung. It was never aired on TV, but they were trying to kind of like explain to people that they should go out and buy 3D TVs. Which is, by the way, that 3D, the notion of 3D TVs is different than the 3D that I mean. And you will see that in a second. So what we call computer vision is basically the science of taking an image, a two-dimensional image, and processing it and extracting some meaningful information out of it, right? Like, say, the location of an object in the scene, the location of a human face, and so on. And you've seen these technologies kind of being more prominent in like new devices, such as consumer cameras, consumer digital cameras, which are, right now I think all of them, or almost all of them, have like a face detection mode, or even a smile mode, right? So when there's actually a smile mode. I've seen this in a camera where you can't take the picture until the person smiles, right? So that's kind of like what we mean by computer vision. The problem with computer vision in terms of robotics is that it's not good enough because it's always poised by false positives or negatives. So in this example, imagine you have a robot, and like we have, and you want to like get a beer from a fridge, and the robot brings back like an empty mug, as you see here, because it matches the template of a beer bottle onto like a picture. That's going to suck, right? It's going to be like, well, this is an empty mug. I want my beer, right? So you're not going to buy that product. You're going to return it back. So, mathematically, this is true. 3D is 50% better than 2D. And we can fight afterwards if you don't agree with me. And, really, again, when we mean 3D, we mean these collections of points that resides in a Cartesian three-dimensional space. So they have an X, Y, and a Z, as we call it. And 3D comes from a variety of sensors. And here's a few examples. And in fact, there's people who are generating 3D by moving a stick on a surface and looking at the shadows projected, right? Which is really cool. And then you have all sorts of like nice things like stereo cameras, time of flight. The Kinect is obviously has made a lot of progress for the gaming industry. But also like very precise like LiDARs, which are used outdoors in mapping. Again, the Google car or like Navtech or Trimble, all these companies doing mapping outdoors and creating these maps. Those are all sources for 3D. And really, again, like when we mean 3D, it's actually kind of like ND because you have like this vector of points and you keep on adding information. And what you saw earlier, if you were here at the beginning, and I'll show it again, this the data coming out from the Kinect is actually more than three-dimensional because it has X, Y, Z, and RGB, right? So in some sense, you could think about it as being like four-dimensional, right? And as we go out and compute like additional surface properties, such as like normals or other things, it becomes even higher dimension. A few examples of where these things are useful. Oops, again, wrong screen. So here you see, this is part of our previous work when I was in Germany. Here you see like a very bulky robot. It has like this cylindrical base, and it's actually using a very heavy laser scanner. If you can see that on one of the up and down, and kind of getting like a 3D picture of the scene. And then afterwards, it's kind of like planning and trying to extract information of where a drawer is, such that you can go and like open it and then search for a particular item, like such as a cup in that drawer. In this case, we're moving a smaller laser unit on a motor here, on a tilting platform. Again, like a three-dimensional point cloud, such that we can actually go and recognize doors and handles and actually go and open them up so we can drive through them. This is part of our, we had a milestone at Willow Garage where we had to other applications in terms of like grasping objects. I've mentioned this previously. So you have to build a three-dimensional map and know the position of each object with respect to each other. Also recognize their label, their class labels from their shape. So this is exactly what the robot sees. It sees this like point cloud, and it tries to fit all these like primitives that it previously acquired or they've been given to it. But there's other more fun projects, such as getting a robot sword and playing Jedi with it. And this is again like all autonomous. There's basically this is a robot arm from Kuka, and what you see in the background is a Kinect sensor, and you're probably going to actually battling with it and explaining the whole thing. So, it's a geeky application, but you could see how this has certain who knows in the future, right? Or whatever you do, training, personal training. One more example here of what you could do with, again, like off-the-shelf, like open-source algorithms. This is a 3D map, a real 3D map of Bremen, downtown Bremen in Germany, northern Germany. And data is acquired using some 3D laser sensors. So you go on a tripod and put them in a certain location. You wait for a little bit. They basically move around and spin and get all this data, and then you move to a different location and so on, and then get another snapshot. And then afterwards, you put them all together through certain techniques that we call registration, point cloud registration. And afterwards, you can create this like immersive virtual 3D fly-through, which again could have multiple applications in gaming or mapping or who knows, like scene assessment and so on. It's pretty cool. And besides the cost of the sensor, which right now is pretty high, the algorithms are actually cheap. Like basically, you can just run it for like an hour. There's many other examples that I don't have time to go through, but you can imagine again, like if you know something about these autonomous. These things don't really come easy, right? Because the way I like to think about 3D data right now, it's in its infancy. It's exactly as we were thinking about two-dimensional cameras or 2D computer vision, 20 years ago or 30 years ago. So we need like a lot of iterations to get these sensors to be better. And to improve our algorithms as well. Okay, so in terms of a tentative solution on moving forward, there's really like two parts. This, again, as I said, like improving the sensors. And here you see some examples from companies such as Microsoft pushing forward for the gaming industry, which is funny. Like we're piggybacking on different industries to get these things happen. But also, I think at some point we're going to go back to stereo. So there's a few cameras, again, coming right now. And I think there's also mobile phones. I've heard about this, like coming with two cameras, which would potentially allow us to reconstruct the world in 3D by doing triangulation, so applying stereo techniques. And when that happens and the costs go really low and everyone has these devices, then we can go back and try to like solve harder problems. And the Kinect basically, if you're into robotics and you don't know about like the Kinect being used on all these robots, I mean, it's just insane. Like people just took it, went to Best Buy, got it, and then installed it on all these different platforms, like even quadrotors that are flying around, heavier ones. And we also think that software is really important because again, like some of these, yeah, go ahead. And I think that's great. It's interesting how, again, like we're piggybacking on different other industries to bootstrap robotics. The gaming industry is one of them, and also like photography and consumer devices is the mobile. I think whenever we see our next generation iPhones and Android phones having like 2 cameras or maybe even more, then I think that's going to like hit another high point. So in terms of software, we had to kind of like change our attitude. So when we started building this all this software for our robots, we always thought that, well, there's like this area called robotics, and there's like personal robotics, and we have different pieces that we should tackle, and 3D perception is just one of them. So like processing 3D data is like really, just like some building block. You get 2 people, and they're going to solve it for you, right? But really, we realized that there's so many other industries, and again, gaming is a good example. I'm going to keep on coming back to gaming. 3D perception is being used continuously. And if you've seen exactly what happens on a Kinect, there's a full-blown skeleton tracker, right? So it's looking basically at all your body parts and estimating their relative position in space, so you can actually go and play those games, right? So 3D perception is just as important as personal robotics, and many things that we don't think of are basically solved by other people. And my personal take on this is that actually, if you solve perception, or if you go towards solving it, that actually kind of like translates to AI, what people think about AI. So if I know my state at all time as a device, as a technical system, as a machine, as a robot, and I know the state of everything around me, like people, objects, and so on, then basically that's like, intelligence. So we've started a project roughly 1.5 years ago. It's called the Point Cloud Library, PCL. And, we're open source basically because our funders kind of like pushed us to do BSD from day one. So all the tools that we build we just give away to the community. And it's actually quite interesting, and we're very excited about it to see big companies taking it and using it, and even startups being created in this space based on our work. But we think that only like tackling such hard problems, you can just not solve alone. You can only do it in a collaborative fashion through open source. So as I said, the name of the project is called the Point Cloud Library, and you can go to this URL and check it out. And the way we kind of like position ourselves is like we want to look at other different areas like industries, like robotics and gaming and mapping and so on, and sort of like take a slice through what we call 3D point cloud perception and build this community. We've tried, like we're big on C++, so we want things to be really efficient. So the whole thing is basically a collection of C++. When we started building this, we were looking at Boost, and we're kind of like aiming to go in that direction, like peer-reviewed, high-quality unit testing, documentation, and so on. And so the whole thing is kind of like split right now into a dozen or so smaller modules, which you can take and use off the shelf for solving some problems, as you will see in a second. This is kind of like a dependency graph, if you're interested in these kind of things, how you could take a component, and that depends on some other components, but eventually you could take like a part of the graph and just use that. You don't have to use the whole tool chain, the whole. All the things that you can actually do with it, again, like off the shelf. So let me play this video here. So here's an example of like real-time online like object recognition. And so one of my colleagues is basically kind of like training the system first by looking at certain objects, and then he's just like pushing a bunch of these objects in the scene. And as you will see, most of the time the system gets them right? Which is again like pretty outstanding. Like 5 years ago, we wouldn't thinking that we would get something like this done, because it again opens up other opportunities later on. There's also some examples here, and you will see actually the label being jittering a little bit, because depending on the angle and the noise model of the sensor and how you train it, it might appear as something else. So that car might be a banana from some direction, which is perfectly fine because we're just looking at a shape, not at the texture, not at the color of the object. More interesting things in terms of segmentation. And I'll show this. And what we're doing here is just trying to get like the edges of the whole scene. We're looking for planar areas. If you think about how autonomous cars and all the research that goes on in that field actually work, they're looking for drivable terrain. So everything that's flat in front of them is good. And that's actually how the DARPA Grand Challenge was solved. So planar areas are extremely important for robotics. And this is what we're doing here, what we call clustering, giving a specific color to each object on the table, which again is important because if you have them separated, then you can go and pick them up. So let's in red over there, it's basically a change detector. Okay, great. So basically I'm pointing the sensor at myself. And as I'm staying still, you're going to see the point cloud being like, just having the RGB color. And as I start moving, you're going to start seeing those particular points in red, right? This is through a technique called voxelization. So we basically subdivide the space into chunks, and then we look at the chunks that move from a frame to another. And you've probably seen similar applications in like security or something like that. We're looking at them from a different perspective. But obviously, again, like this has, once you solve this problem, it has like multiple applications. Going outdoors, getting these partial views, and kind of fusing them together. And these are again tripods with lidars scanning, and software that runs under the hood to try to optimize them and find like the best correspondences between those two to create like a consistent map. And you can imagine like at a city scale, you have to put lots and lots of these together to make. Recently, we've been exploiting the Kinect for other applications. Who actually heard about the Kinect Fusion application? Okay, there's a So what this application actually does, what we're trying to do here is exactly what you mentioned earlier, is sort of create together multiple frames and create like a 3D map of the scene. So you start from one particular viewpoint, and as you move the camera around, you start integrating that other information. Actually, maybe I can look at you directly. Let's see if I can. And the cool thing is also that like the more we look at a particular scene, the more we can smooth out the data and correct for sensor inaccuracies. And so after a while, it'll appear like the data is going to be like less noisy, and it's going to be like closer to the real surface. Right? And you can play with this. I can show you afterwards how to download it and play with it offline. Personalized like 3D maps. Just move one of these sensors around in a room, get enough pictures, and then put them all together through using our software, and kind of like map your world. Why not? Why do we have to expect the big dogs like Google and Trimble and Navtec to map things around us when we
In this video, we introduce continuous.
Where, again, you're going to see our
areas of the world outside that volume are
bending it a little bit towards larger scenes.
The volumetric model in space.
So they're just moving around.
Allowed to move with the camera. As the volume moves, instead of
office environment, and I think they also have like some other examples
we
afterwards.
implement a set of cyclical indices.
Or just skill maps, not just like room size, but
This window so dark with a complete part with moving. The final point cloud contains 1.4.
Actually went the stairs, so they went, from one floor to another, which is cool. And I only do this with 3D, obviously, because, if you take like a panorama in 2D, it's only going to be like 360, and that's it. There's no like depth to it. You can't go like up and down.
In spite of the scale of the tank.
Using real
Use something regarding object tracking, which is another.
time tracking algorithm.
This involves like getting a particular object model and then moving it around in space and continuously tracking it, right? These two techniques called particle filters. I don't know how many of you have done like probability or statistical classes, mathematics. Okay, a couple. Well, particle filters, hopefully all of you will learn about them. They're very important tools that allow us to kind of like basically build hypotheses and evaluate them in parallel really fast and get better results for algorithms such as tracking. There's other many things. Again, I'll skip through some of these things like vegetation classification or scene assessment. Building triangle meshes is also important for us. And also getting, particular labels for the stems or scenes so that when the robot's going grasp, then they grasp them from the right position, not from just anywhere. I'll skip through this. What I mentioned with skeleton tracking, we also have our own open source implementation of a skeleton tracker. It is basically different body parts being kind of trying to keep the same consistent color, the same consistent label as you move in space, right, as you go through time. And if you can do that reliably over multiple frames, then you get your skeleton tracker. And then you can. GUIs are also something that we're working with a lot of students, part of the Google Summer of Code project. So we've been doing a lot of like GUIs lately in terms of like editing point, like a Photoshop for point clouds, if you want, something like that. Supported our software to Android and iOS because that's basically where basically what we're doing here, I'll show you. This is an iPad, right? It's nothing fancy. And we're running the software for visualizing point clouds and processing, doing some basic processing directly on the device. And it's kind of cool because tablets also offer a very interesting way of navigating, manipulating point clouds. Like in 3D, it's very natural to kind of like rotate around and kind of like see what's going on, right? Otherwise, it's a bit more cumbersome, I think. And I think I mentioned this earlier in terms of like finding planes. So one application that we're very interested in is like finding the biggest dominant planes in a scene, because those are most likely the ones that are going to support objects or the ones robot. And one thing that we also learned is that these devices actually have a lot of processing power. So you can run some of these things in near real time on them. If you're interested, we can talk about it more afterwards. A Kinect, or for those of you that might be familiar with the Kinect's sister, there's an Asus camera, which is basically lighter and it only has like one USB to an Android tablet and doing processing directly on the tablet. So you can get data there, visualize it, and also do some processing directly on board. So we're also doing a lot of visualization on the web. Again, because this is kind of like a hot subject these days, so doing WebGL and visualizing large-scale point clouds online is very important for our community. Building complete models is kind of fun too for like toys. The things that I want to show is that we've been encouraging our developers to sort of like blog almost on a daily basis and post those results online so that like everyone, like people don't have to wait between releases or go to scientific conferences to get this like information. They can just like go online and like access it and then afterwards email the developers or email the mailing list and talk to them directly. So here you see just me kind of like scrolling down on our blogging website, and you see all sorts of things from technical reports like PDFs to like code snippets, pictures, instructions on how to run certain tutorials, and on all sorts of different fields. Like the topics covered here are very broad because our community is basically looking at multiple applications, multiple different angles. You're probably going to see some videos at some point. And I think I do have a short example on visualizing point clouds online on the apps and an analysis of different features and different one of the things that also surprised us is to see such a big involvement from the academic community. So we only launched, if you can call that a launch, I mean, it's an open source project, right? It's not like we went out on Engadget or anything like that. It was only like 1.5 years ago, and we got, roughly 450 developers, as you will see shortly, coming from over like 50 institutes around the world, kind of contributing to this project. Some of them are kind of like grouping up, pairing up already, creating startups in this field. Others are working at like more established institutes, or big companies like Toyota and Trimble and NVIDIA. And I was actually looking at these graphs the other day. It's kind of funny to see that we have, on average, we get like 20 new developers a month. It's almost like it's almost like one a day, And people just kind of come together and, pretty much devote a lot of their time. Some of them are PhD students, some of them are engineers, some of them are undergrads. Just because it's kind of like cool to play with this sort of data and learn a lot while doing so. You've probably seen a lot of like open source talks today. I want to bother you like why should you do open source, but if you still have doubts, talk to us afterwards. We'll convince you. And so it's nice because we also have involvement with the industrial partners. So they come to us and we create these things called code sprints. A code sprint is nothing else than a Google Summer of Code project. But instead of like waiting for the next summer, because the summer just ended, we're kind of like doing it all year long. And we pay, these companies pay in the same manner, the same way that Google does. So we do like every 3 months of work, and you get to be paired up with one of the developers in the community, and again like learn a lot from them and have a lot of fun. And so we're doing this right now with I think 10 companies or something like that, which is more community outreach instead of like going to conferences. I don't think you guys go too much conferences yet, but hopefully you will in the future. There's a few good ones out there, and I strongly recommend you go, and you're probably going to like find us there and talk to us there. You guys know what Gorge is, right? Hopefully. A visualization tool that helps you kind of like track what's happening with the history of your repository, of a particular repository. So the way this works is, every little file in your repository is like one of those like small dots, and then directories are branches, and all those pictograms kind of like jumping back and forth are developers. And I usually like to show this to whenever I go and give out talks, because what it shows is that we can only do this if we work all around the globe like 24/7. Like if we would only work in California for like 8 hours a day or 10 hours a day or 12 hours a day, we couldn't build this library as fast as we did, right? Or this set of tools. By going like completely global, then you have like, you work in the US, then you go to sleep. People in Europe wake up, they start hacking, they go to sleep. Asia wakes up, start hacking. And by the time you wake up, it's like, wow, all this code that I have to review now for the next day. So it's kind of cool. And one of the things that we've also been doing is developer meetups. So getting people in certain geographical locations to meet up and discuss all sorts of things. That actually also contributed to the growth of the project. So in my opinion, this is what I want to be. This is where I want to go. If I get a robot to understand and watch TV, that's perfect. We solved the problem. If a robot understands TV, that's solved. And I'll show you a fun videos. I don't think you've seen this yet. This is one of the projects that one of our founders was trying to push forward. He had this like weird idea of doing a competition with a robot. So, and he posted an announcement and said like, whoever can come up with like the craziest and most fun idea wins like whatever $10,000 or something. Our colleagues from Berkeley came up with this idea of like pairing up socks and flipping them and putting them together. And this is a video that won the competition. And it's kind of like fun to watch it, I guess. It's all doing it, you know, autonomously, which is pretty cool. Yeah. Okay, so with that, basically, I do want to say one thing. This is a completely brand new area. Like, you know, it's so new that like most universities don't even have classes on it. There's just nothing that kind of like teaches you about like 3D perception yet or 3D point clouds. And I think the only way to go forward is through maybe a larger community of contributors and not so much through university, courses. We think that working together on open source is the way to go. There's just no other way. Like if you sit by yourself and you try to solve it, forget about it. I mean, maybe you're super smart and you can do it, but you know, we certainly couldn't do it ourselves. And one thing that I don't want to say with respect to open source, because I heard a lot of talks today and I heard like pros and cons, and people were like, you know, some of them were bashing open source, some of them were like pro open source. From our experience, the only way that you can build your career up, or one of the ways that you can build your career up, is actually to put yourself out there online and kind of like do open source. As a company, most employers right now are going to be looking at like your online profile. What did you do, right, through your career? Because if you only take a person and try to interview them in like a couple of days, like what can you learn from them? Like how much can you learn from them? But if you look at their, you know, track history of commitments or something, or commits to an open source project, and you see how they reacted on mailing lists and whether they're, you know, they were like assholes or they were like, yo, really friendly, right? That kind of gives you a better indication of the person and whether you want them in your team or not. So I think you should really consider doing some open source in your career as an undergrad student. Just my take. With that, I thank you for your attention, and I will take any questions if you have. Thank you. That's a great question. We're mostly doing our things on CPUs, but one of the demos that I just showed, the one with the Kinect Fusion demonstration, that's actually running on a GPU. And that's the only reason why I carry this like 50-pound laptop with me, because it has like a beefy GPU on it. So we do CUDA processing most of the time for like fast real-time applications. If we could assess the state of the world and like in real time, I think planning would be so much more easy. It speed ups on all those operations. Whenever you would like, if you go back and watch the video, you're going to see like at some point like a 20x like on the video. That's when it was like sitting on top of the next to the fridge, looking at the beer bottles and trying to like assess like which one is which and so on and so forth. So it's all perception. I think a little bit of everything, to be honest. I think our algorithms, I mean, we're barely scratching the surface. There's just nearly not enough people like working on these problems. And honestly, yeah, I think if we would get, you know, I know the new GPUs from NVIDIA have like, you know, 2,000 cores or something, the new Kepler cards. If you get like more cores, all our tasks are highly parallelizable, by the way, because we do like per point operations. So whenever you have like, you know, thousands of points, having thousands of cores would help. And I think it's, so there's two things. Again, perception is the limiting factor there because we're always trying to assess what's happening around us so we don't collide into things. So we need like, you know, faster algorithms for that. The other thing, like from some of the videos that you've seen, the PR2 was built up so it doesn't move too fast because it's supposed to be working in the presence of humans. There's other robots that move actually faster, and you might have, if you've paid attention to the video with a lightsaber, that cook arm can move really fast. But perception is the bottleneck there. Like, I think if we make that fast, the robots will move faster in the end. Give me an example so I can.
I mean, I see this thing on
So if I understand right, well, so I have a different take on biologically inspired. I try to stay away as much as possible from like the classical artificial intelligence and replicating the human brain the way people do it, because I think that's not necessarily how we're going to solve this problem. I think we should be looking at more like engineering kind of things in the long run. As humans, I mean, it's easy, right? Like, we're babies, we learn like, 4 years, then we get told like, well, this is that, and so there's this reinforcement learning that we apply to ourselves. I don't think this is kind of like translatable one-to-one to robots yet, in my opinion. So the way I would like to see problems like this solved is through more engineering than like biologically inspired kind of things. Me too, yeah. I mean, we have to downsample sometimes to like, QVGA or QQVGA or something, because these cameras are VGA. But the problem that you have there is when you start losing too much information, it's a curve, right? You start losing too much information, then your processing basically becomes useless because now you're not extracting the information that you want from it. So it's kind of like there's a trade. Absolutely. And you're right. We actually do that quite a bit for multiple applications. For example, for extracting planes, we downsample like crazy because, from three. But other things, again, like an object, like if you're trying to differentiate between, let's say, a glass, only have a few points on the handle of the mug, then it becomes tricky. So there's two techniques that you usually can apply. One of them is actually probably available on everyone's phones right now if you guys are familiar with the Google Goggles application. So what that does is like it looks at a picture and it tries to actually read the text, like it does like text recognition. And once you do the text, then you can just like parse the text and you say you there's a label, you read it's like some juice bottle, like Odwalla, and then that's it. You search for that. The other approach is for every little point in space, little pixel, you take a surrounding area, right? You take a group of pixels, and you compute what we call the feature from it, like a vector from that, and then you train systems using those vectors. So whenever we look at an object and we recognize it, we basically do nothing else but match a group of those regions that we saw. Fonts don't matter there. So the PR2 sensors are, and I'm sorry I didn't have enough time to go through that. The PR2 sensors are, we have two stereo cameras on the head, one wide angle, so you can look more like this, and one narrow to be focused on objects. And then there's basically two laser sensors, small ones. There's a company in Japan called Hokuyo. And one of them we actuate like up and down to basically get like a sweep of the whole scene. And then another one is like planar, so it only sees in front of it. First tend to work up to let's say like 10 meters with some accuracy of great for indoor applications. When you go outdoor, however, like usually, especially for like things can move fast. That's one thing, right? So if you have like a car driving around, you want something that sees more in front of it and faster. And there's sensors such as the Velodyne. It's like this spinning, 360 LiDAR. And like this is probably something that you might have seen on Google cars already, like the ones. Those are more suitable for those things. Also outdoors, one of the problems that you have is different weather conditions. So you have to look at sensors that are, can cope with. Indoors, it's mostly like nice and cozy because we instrument environments. I think it's the whole process, like just building it in California. It's just really expensive. There's like getting all research and development there. That wasn't really fair. There's actually there is a discounted version. So the way our founders were looking at this problem, they said, well, if someone is willing to do open source, we're going to offer them a huge discount, like 100 and I think at some point they said, well, what if we chop off like one arm? So like you only get the robot with one arm. Well, okay, it's half the cost, right? I mean, first of all, I think we're not mass producing them. I think that's a big problem. If you could get like if this would be a clear product and people would really want to buy this because it would do useful things, or not end users, let's say companies, and you could get like a nice assembly line, a manufacturing line in a, it would go down in price. And I know there's a few companies right now trying to do that, but in different applications. But yeah, I think basically there's two things, like building it in California and like not mass producing it are the limiting factors. So the library that we put together is all C++. We're really, really hardcore in C++. We love it. I think it's the best thing since sliced bread. It's very complex and very shitty for multiple things, but it does the job. We need our code to run as fast as possible, so compiling is key here. For higher level things, such as, once you get a state of a role, like planning a motion or something, you can use Python or Lisp. Oh, not at the moment. We're trying to be as agnostic as possible with respect to the data sources or the computational platforms. Because we're still in this like non-profit, kind of like, funky way where, we're just trying to grow this set of tools. Later on, I could see, a lot of people from the community building for-profit startups and going for like tackling specific problems. But like right now, we're not looking. Questions? Thanks again.